Hello again. So in this session, I'm going to solve another example to find the velocity potential for a source flow. So the question is as follows. Find the velocity potential of a point source flow. So this can be a point source flow. This can be, for example, this can be a gas pipe with a hole in it. Okay. So let's get started to see what is a source flow. So a source flow is like something like this. This is a source. For example, if there is a hole in a gas pipe or in a even water pipe, the flow will leak something like this, and now we want to find the velocity potential for this type of flow. Okay. So in this type of flow, the flow rate that goes at each radius with respect to the center is constant. So the volume flow rate that we show with Q at each, say, radius R, this much of the volume, because this is like if you have a hole, say, in a water pipe or gas pipe, how much flow is going out, the volume flow rate is kind of constant. So here we can say that at any arbitrary R, here, if this is your R, the volume flow rate that is going out of this, say, control volume with radius R is constant. So what is the volume flow rate here? It's going to be the perimeter of that 2 pi R the area times the velocity. So we can say if we have a velocity, a radial velocity here, like ur, how much of the flow is going out, right? So you need to multiply velocity by area to get the volume flow rate, right? So this is kind of the perimeter, and then in order to get the area, we have also another dimension, which is kind of the width. So this is going to be the area. So I just ignore that. So I only have the perimeter times UR, which is going to be constant. Okay. So because this is constant, so we can say that the velocity, the radial velocity in this type of flow, point source flows, is going to be Q over 2 pi R. And we can assume that this is symmetric flow, so u theta, the tangential velocity is just 0. So that means that there is no velocity in this direction, okay? So we don't have any velocity in this direction, or the tangential velocity is 0, and then the radial velocity is going to be this, okay? So this is kind of a source flow, okay? So in order to find the velocity potential for this flow, the first question that we want to answer is that, is this flow irrotational? Okay. In other words, is the curl of velocity vector for this flow 0? So we need to answer this question before moving forward with the velocity potential to find a velocity potential, and if there is any velocity potential exists for this. So because you see these, we wrote the velocity components in radial and tangential components, or in other words, in cylindrical coordinate. I want to talk a little bit about cylindrical coordinates and how we define the curl of velocity in a cylindrical coordinate, because there are some differences between cylindrical and Cartesian coordinate, which is the typical coordinate system that we use. So let's get started on cylindrical coordinates. So we want to see what is the vorticity vector or curl of velocity in these kind of cylindrical coordinates, okay? So let's define a cylindrical coordinate for those who don't remember. So we can define it as follows. So this is the a typical Cartesian coordinate system. So it's x, y, z. So x, y, z. And now I want to define a cylindrical coordinate. So here, say I have a point. I want to kind of represent this point in cylindrical coordinate, not in the Cartesian coordinate. Okay, so let's see. Let's say it is here. So the first thing we are going to do, the z is the same in both coordinates, okay? So you just come down to the xy plane, and this will give us the z coordinate. And then what you are going to do is, in this type of, in this coordinate system, is that from the center, you will find the distance with the point where that reaches to the xy plane, okay? So we call this component r, or the radius, and then we call this angle theta, and this distance is just z. Okay, so this point, we show it with these three components in the cylindrical, with the radius r, with the angle theta and with the height z. Okay, so instead of x, y, z, we just show it in cylindrical coordinate with r, theta, and z. Okay, so now that we know this, I want to write the momentum equation first in Cartesian and then in cylindrical coordinates, okay, coordinate system. So in the simple Cartesian coordinate system, that this is what we typically use, the momentum equations are as follows for an inviscid flow. So the momentum equation for an inviscid flow in Cartesian coordinates. So it's going to be partial u over partial t plus u partial u over partial x plus v partial u over partial y plus w partial u over partial z equals to minus 1 over rho partial p over partial x minus g x. And remember, this is just the Euler's equation, but now I'm writing all the three components. This is in the x direction, so x direction. This is in the y direction. So it's going to be partial v, partial t plus u partial v over partial x plus v partial v over partial y plus w partial v over partial z equals to minus 1 over rho partial p over partial y minus g y. And then in the z direction, it's going to be partial w over partial t plus u partial w over partial x plus v partial w over partial y plus w partial w over partial z equals to minus 1 rho partial p over partial z minus g z. Okay. So this is momentum equation for an inviscid flow in Cartesian coordinate. And now let's see the momentum equation in cylindrical coordinate system. Okay. So for cylindrical coordinate system, so here we had u, our velocity vector is u, v, w, and for a cylindrical coordinate system, uz is the same, or w is the same, but we also have ur and u theta, the tangential, and the radial velocity component. So our velocity vector is going to be ur, u theta, and uz. Okay, so I want to write it now for these. So the first component is for the radial velocity is going to be, so the r direction is going to be partial ur over partial t plus ur partial ur over partial r. And you can derive this. I'm not going to drive it here, but you can actually drive this by a transformation from Cartesian coordinate to a cylindrical coordinate. Plus, I just write the final answer that after the transformation, how does it look like? It's going to be u theta over r partial ur over partial theta plus uz partial ur over partial z minus u theta square over r equals to minus 1 over rho partial p over partial r minus gr. And then in the theta direction, it's going to be partial u theta partial t plus ur partial u theta over partial r plus u theta over r partial partial u theta over partial theta plus uz partial u theta over partial z plus ur u theta over r equals to minus 1 rho partial p over partial theta minus g theta. Okay, so this is in the theta direction. And then in the z direction, we have partial uz over partial t plus ur partial uz over partial r plus u theta over r partial uz over partial theta plus uz partial uz over partial z equals to minus 1 rho partial p over partial z minus gz. Okay, so this is going to be the momentum equation in the cylindrical coordinate system. And another important kind of expression for in cylindrical coordinate is that for a given function in cylindrical coordinate system, the gradient of that function is calculated as follows. So say we have a function f, which is a function of r, theta, and z, and the gradient of that is going to be partial f over partial r, the first component. The second component is 1 over r, partial f over partial theta, and then the third component is partial f over partial z. Or in other words, if I want to write it in vector form, it's going to be partial f over partial r er plus 1 over r partial f over partial theta e theta unit vector plus partial f over partial z ez. Okay, these are like ijk in the Cartesian coordinate. Okay, so this is another important thing that we need to know in cylindrical coordinate if you want to use this cylindrical radial and tangential velocity. Also, curl in, let's say, curl operator. So this was grad operator. So this is grad operator. And this is curl operator in Cartesian and cylindrical coordinate system. Let's see what are they. So in a Cartesian coordinate system, the curl of velocity is just the cross product of grad and the velocity vector, right? And we know from algebra that the cross product of two vectors is just the determinant of I, j, k, and then those two vectors, right? In a Cartesian coordinate system. So the first one is the grad, which is partial over partial x, partial over partial y, partial over partial z. And then the second one is the velocity vector, which is going to be u, v, w, right? So this is in the Cartesian coordinate system. And now let's look at this in the cylindrical coordinate system. So in cylindrical coordinate system, the curl is going to be like this. You can calculate it yourself, but it's going to be 1 over r. The determinant of this matrix. So first row we have ER, the unit vectors, R, E theta, and EZ. And then we have partial over partial R, partial over partial theta, and partial over partial Z. And the velocity vectors are UR, RU theta, and UZ. And so this is in the cylindrical coordinate system. So in cylindrical coordinate system, this is going to be the curl operator, okay? So vorticity vector in cylindrical coordinate system based on this, and we know this is the grad, right? The grad was, as you can see, I just used this formula here. Okay. And here you can see that the vorticity vector is going to be, if you calculate it here, say for the first component, if again for those who don't remember, this is the way we are going to calculate the determinant for this matrix. So for the first component ER, you first write it down, ER. And then you are going to calculate multiply this by this, and then subtract it from multiplying this by this, okay? So this is the way I'm going to do that. So it's going to be partial. And also we have 1 over r here, so I'm going to write it down. So 1 over r, partial uz over partial theta, minus r times 1 over r, so that's going to cancel out. So we only have partial u theta over partial z. Okay. And then similarly, you can do this for the second component, but now we have also a minus sign for the second component, if you remember from your algebra. It's partial UR over partial Z minus partial UZ over partial R E theta. And then the third component is going to be 1 over R partial RU theta over partial R minus partial UR over partial theta Ez. Okay? So this is going to be the vorticity vector in a cylindrical coordinate system. So now let's go back to our earlier question and answer this. Is this flow irrotational? So for irrotational flow, vorticity vector should be 0, so the curl of the velocity should be 0, and this means that all these components should be 0. So 1 over r partial uz over partial theta must equal partial u theta over partial z, and partial ur over partial z must equal partial uz over partial r, and partial ru theta over partial r must equal partial ur over partial theta. Okay, so let's go back to the point source flow problem that we had. So for that problem, UR, if you remember, is Q over 2 pi r. U theta and UZ are just 0. So UR is Q over 2 pi r, and U theta equals to UZ equals to 0. Okay. So this means that we only have one component here, right? Because U theta here is 0, so we don't have this. Let me see. U theta and UZ is 0, so we don't have this. And for the other component, we can calculate that. So let's say for the third component, which is the vorticity vector in the z direction, is going to be, if I want to write it down, it's going to be 1 over r partial ru theta over partial r minus partial ur over partial theta. Okay, and we know that partial u theta is 0, so this component is going to be 0, and partial ur, the derivative of partial ur, which is this function with respect to theta, what is that? It's just 0. It doesn't have any theta component and dependency in itself. So this omega z is going to be 0. And so our vorticity vector is going to be 0, and this is an irrotational flow based on what we define and what we found from the curl of velocity in the cylindrical coordinate. So it is irrotational. So now that it is irrotational, we can actually find the velocity potential for this problem. So let's see, what are the velocity potentials here? So we have UR. So UR, which is going to be in terms of, if you want to write the velocity potential, I think I already wrote that. So it's going to be grad of phi, right? So for grad of phi, UR is going to be the first component of that. So here we have it. So for the first component, if we have grad, is going to be grad phi over grad R, right? So it's going to be partial phi over partial R, which equals to Q over 2 pi R from here. So now it's simple integration. So phi is going to be Q over 2 pi logarithm of R. Okay. So this is going to be a source flow. And we can also have a sink flow where the velocity vectors are in the opposite direction. We just need to add a minus sign here. So it's going to be minus Q over 2 pi ln of R, which is going to be a sink flow. Okay. So let's see how does this look like, the velocity potentials. So as you see, the velocity potentials are only a function of radius, right? So as the radius increases, those velocity potentials are also increase. So let's say the first one, I can show it like this. Let me maybe do, it's better if I do it with this, it's easier. This is the first one. And then the second one, I can do it again here. Okay, so these will increase by R. So this is, let's say, phi 1. So let me decrease this. This is phi 1, and this is phi 2. And phi 2 is going to be larger than phi 1. Okay. So these are actually going to be the velocity potentials, right? If you wanna plot those velocity potentials, this is how they will look like in the source flow. Okay, so this was the second example of a source of finding the velocity potentials. So in the next session, I'm going to introduce the string function. So let's have a review what we learned today. So we introduced the rotation in the inviscid world by defining velocity potentials, which is going to give us some analytical solutions for inviscid flow, inviscid rotational flows, right? And also we assume if we have, so we define this phi, because curl of grad is 0, so we can define a velocity potential as this, okay, which is going to be perpendicular to the velocity vector, and the velocity goes from low potential to high potential, okay? Also, if we found if this flow is incompressible, then this kind of satisfies the Laplace's equation, which is going to be a linear system, which we can find and solve it analytically. Then I solved two examples of velocity potential, one for a uniform flow, which we found is just phi equals to ux. The velocity potential is going to be just ux. And then for the source flow, I just went through the cylindrical coordinate basics and fundamentals. So what are the momentum equation there, and also the grad operator, and also curl operator, and what does the rotationality entail in this kind of coordinate system, the cylindrical coordinate system. And then we went back and found this velocity potential for a source flow, which could be like if you have a leak in a gas pipe or in a gas pipe or water pipe. This is going to be how the velocity is going to go without just in viscid world. Just remember, if we don't have any viscosity, this is how it's going to go, and then the velocity potentials is just going to be partial phi over partial r, which is going to be the phi is going to be q over 2 pi ln r. So it's just increasing with radius logarithmically, right? So this is how it looks like. And again, in the next lecture, I'm going to introduce stream functions, which is another technique for 2D incompressible flows, where we can actually find some analytical solutions for the streamlines of the flow. Thank you very much, everyone.